everyone, welcome to Business Statistics class. So in today's video we will study a new concept, that is conditional probability, and other important definitions, and also we will solve some more problems. So let us see what is conditional probability. Let A and B be two events, then the conditional probability of B given A is the probability of happening of B when it is known that A has already happened. So from the name itself we understand that there is a certain condition imposed on an event. So here the conditional probability of an event B given an event A, that is we know already about the event A. So therefore the probability of happening of B when it is known that event A has already happened. So on the other hand, the probability of happening of B when nothing is known about happening of A is called as unconditional probability of B. So the conditional probability of B given A is denoted by probability of B given A. So this is not a slash, this is a straight line. So that is this is read as probability of B given A. So let us see how to calculate conditional probability. So the condition is the probability of A should always be greater than 0. Then the conditional probability of the event B given A is defined as probability of B given A is equal to probability of A intersection B divided by probability of A. So here we know that we already know that an event A has occurred with probability given as probability of A, which is always greater than 0. Then the conditional probability of event B given A is probability of A intersection B divided by probability of A. And if probability of A is 0, then the conditional probability of B given A is not defined. If A and B are independent events, occurrence of B will be independent of occurrence of A. Therefore, the conditional and unconditional probabilities are equal. So the conditional and unconditional probabilities are equal only when events A and B are independent events. That is, probability of B given A is equal to probability of B. So probability of B is equal to probability which is equal to probability of A intersection B divided by probability of A. Therefore, probability of A intersection B would be probability of A into probability of B. That is, probability of A is taken to left hand side. So let us see what is independent events. Two events A and B are independent if and only if probability of A intersection B is equal to probability of A into probability of B. So we can say two events are independent only when probability of A intersection B is equal to probability of A into probability of B. So if two events are independent, the occurrence or non-occurrence of one does not depend on the occurrence or non-occurrence of the other, because both the events are independent. So in previous classes we had seen about addition theorem. So now let us see what is multiplication theorem. Let A and B be two events with respective probabilities, that is probability of A and probability B. Let probability of B given A be the conditional probability of event B given that event A has happened. Then the probability of simultaneous occurrence of A and B is probability of A intersection B, which is equal to probability of A into probability of B given A. So if they'll ask you about the multiplication theorem, then it is important to write this particular equation, that is probability of A intersection B, which is equal to probability of A into probability of B given A, because we know that event A has already happened. So if the events are independent, the statement reduces to probability of A intersection B would be probability of A into probability of B, because we had seen when the events are independent, then probability of B given A would be probability of B. Therefore, probability of B given A is substituted as probability of B. Therefore, the multiplication theorem reduces to probability of A intersection B as probability of A into probability of B. So these were three important definitions. So now let us solve some problems. So the 14th problem is, a card is drawn at random from a pack of cards. What is the probability that it is a heart? And the second sub-question is, if it is known that the card is drawn red, what is the probability that it is a heart? So this is an example of conditional probability, because we know that a card drawn is red, then we have to find out what is the probability that it is a heart. That is, one event has already happened, we have to find out the probability of the other event. So they have given from a card is drawn at a random from a pack of cards. So therefore small n is equal to 52, because there are 52 equally likely outcomes. So let us calculate the first sub question, that is probability that it is a heart. So let event A be a card drawn as a heart. So this is an unconditional probability of drawing a card, because no other condition is imposed. Therefore probability of A would be 13 divided by 52, which is 1 by 4, because there are 13 heart cards in a pack of cards. Among these, any one card can be heart. Therefore 13 divided by 52, which is 1 by 4. So for the second sub question, let us assume event B as the card drawn is red. Therefore the conditional probability of drawing a heart given that it is a red card is probability A given B, which is equal to probability of A intersection B divided by probability of B. So here we know that event B has already happened. We have taken that event as to be B. So we have to find out event A given that event B has already occurred. So event A is that the card drawn as heart, given the card drawn is a red card. So in a pack of cards, we know there are 26 red cards. Among that, we have 13 favorable outcomes, which has 13 hearts. So 13 hearts are red and 13 hearts are diamond. Therefore probability of A intersection would be 13 divided by 52 whole divided by probability of B is, that is the card drawn as red, is 26 by 52, because there are 26 red cards. So we have substituted it in the problem of conditional probability. Therefore 13 divided by 52 whole divided by 26 divided by 52, we get it as 1 by 2, that is 13 divided by 26, which is 1 by 2. So here we got the probability of A intersection B as 13 by 52, because event A intersection B has 13 favorable outcomes, because when any of these 13 hearts is drawn, A intersection B happens. So the next question is, a fair coin is tossed thrice. What is the probability that all the 3 tosses result in head? So now let us assume event A to be the first toss results in head, B as the second toss results in head, and event C as the third toss results in head. So whenever you toss a coin, the possibility of getting would be either head or tail. So here when we toss the first coin, we have taken event A as the first toss results in head, similarly B and C. So since A, B and C are the results of 3 different tosses, they are independent. Because head and tail cannot appear together, therefore it is an independent event. The probability that all 3 tosses result in head is, that is probability of 3 heads, which is probability of A intersection B intersection C. So because each of the 3 tosses are done at different time, they are independent, we had seen, and since they are independent, we can write probability of A intersection B intersection C as probability of A into probability of B into probability of C. So we had seen this in the definition of independent events. So for 3 events, the independent event would be probability of A into probability of B into probability of C. So for event A, when you toss a coin, to get whether it is head, we have the probability is 1 by 2, and for getting tail, the probability is again 1 by 2. Therefore, for event A, the probability is 1 by 2. Similarly, when you toss a coin for the second time, so the probability of getting head is again 1 by 2, and for probability C, the answer is 1 by 2. So since we have taken intersection, we have to multiply, that is 1 by 2 into 1 by 2 into 1 by 2, which is 1 by 8. Therefore, when you toss a coin 3 times, the probability that all the 3 tosses result in head is 1 by 8. The 16th question is, 2 fair dice are rolled. If the sum of numbers obtained is 4, find the probability that the numbers obtained on both the dice are even. So even this is an example of conditional probability. So let event A and B be. Event A is the sum of numbers is 4, and event B is the numbers on both the dice are even. So here event A has already happened, that is the sum of numbers obtained is 4. It is already given. And we have to find out that the numbers obtained on both the dice are even. Therefore, we have to find out probability of B given A, which is probability of A intersection B divided by probability of A. So event A has 4 favorable outcomes, namely 1, 3, 2, 2 and 3, 1. That is, when you add this, you have to get the sum 4. So among the sample space, we have 3 outcomes which are favorable to event A. That is 3 plus 1 is 4, that is the sum is 4. Similarly, these two. Therefore, probability of event A, that is the probability of sum 4, is 3 divided by 36. So here small n is 36 because we are rolling 2 dice, that is 6 square, which is 36. And event A intersection B has one favorable outcome, namely 2, 2. So A intersection B means the sum has to be 4. Also on both the dice, the numbers should be even. So in all these 3 cases, there is only one favorable outcome, that is 2, 2. So here the sum is 4. Also the 2 numbers are even. So here these 2 numbers are odd, and even here these 2 numbers are odd. Therefore, A intersection B has one favorable outcome, which is 2, 2. Therefore, the probability of sum 4 and numbers are even, which is probability of A intersection B, is 1 by 36. That is number of favorable outcome divided by total number of outcomes. So 1 by 36. Thus, we can find out probability of B given A, that is numbers even given the sum is 4. So we got probability of A intersection B, and we know the probability of A. Substitute. Therefore, probability of A intersection B is 1 by 36 and probability of A is 3 by 36. Therefore, probability of B given A is 1 by 3. So these are some important note. The first note is the probability of a null event is 0. So null event is denoted as by Therefore, probability of phi is equal to 0. The probability of a certain or sure event is 1. The third notice, the probability of sample space is 1, that is probability of capital S is 1. If A and B are mutually exclusive events, the probability of A intersection B is 0. So when two events are mutually exclusive, then their intersection will always be, then the probability of the intersection will always be 0. So the 17th problem is, if probability of A is 0.3 and probability of B is 0.4 and probability of A intersection B is 0.2, we have to find out whether A and B are independent. So we know that event A and B are independent if and only if probability of A intersection B is equal to probability of A into probability of B. So here we have probability of A intersection B as 0.2. Therefore, let us substitute all the values in this and check whether they are equal or not. So probability of A into probability of B is 0.3 into 0.4, which is 0.12, which is not same as probability of A intersection B. That is, probability of A intersection B is not equal to probability of A into probability of B, which means that A and B are not independent. Suppose this condition was satisfied, then we could say event A and B are independent. So the 18th question is, if probability of A is 0.7, probability of B is 0.46 and probability of A union B is 0.93, find probability of A given B. So to find it should have been B given A. So to find probability of B given A, the formula is probability of A intersection B divided by probability of A. So whatever event has been happened, you have to take it in the denominator. Don't get confused. So therefore, probability of B given A is probability of A intersection B divided by probability of A. So we already have probability of A, but in the question we don't have probability of A intersection B. So first let us find out probability of A intersection B. So we know by addition theorem, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So we want probability of A intersection B. Take it to left hand side and A union B to the right hand side. So the new equation would be probability of A intersection B is equal to probability of A plus probability of B minus probability of A union B. Substitute the values and solve for A intersection B probability, which is 0.23. So now we got all the values. Therefore, probability of B given A would be probability of A intersection B, which is 0.23, divided by probability of A, which is 0.3286, and probability of A given B would be probability of A intersection B divided by probability of A intersection B divided by probability of B. So we know probability of A intersection B, which is 0.23, and we know probability of B, which is 0.46. Therefore, 0.23 divided by 0.46 would be the answer for probability of A intersection B. So the 19th problem is, probability of A is equal to 4 by 5 and probability of B is 1 by 2. If A and B are independent, find probability of A intersection B. Also find probability of A union B. So since A and B are independent, we know that probability of A intersection B is nothing but probability of A into probability of B. Substitute the values of probability in probability B. So we will get probability of A intersection B as 2 by 5. So then to find out A union, probability of A union B, we can use the addition theorem. Therefore, we know probability of A union B, which is probability of A plus probability of B minus probability of A intersection B. So substitute the values. Therefore, probability of A union B would be 9 by 10. So the 20th question is, a bag contains 5 tennis balls and 4 cricket balls. 3 balls are drawn randomly from the bag. Find the probability that all the drawn balls are cricket ball. And the second sub question is, at least one of the drawn ball is a cricket ball. So the bag totally has 9 balls, that is 5 tennis ball plus 4 cricket balls, which is 9 balls. So among these 9 balls, 3 balls are drawn randomly. Therefore, there are 9 C3 equally likely ways. So from 9 balls, 3 balls can be selected in 9 C3 ways. So for the first sub question, that is all drawn balls are cricket balls. So 4 C3 selections will have only cricket balls because there are only 4 cricket balls. Among these 4, we are choosing 3 balls. So the favorable outcome would be 4C3. Therefore, the probability of getting all the drawn balls as cricket ball is 4C3 divided by 9C3. So here I have shown how to simplify the combination answers. So here 4 factorial divided by 4 minus 3 factorial into 3 factorial divided by 9C3 is 9 factorial divided by 9 minus 3 factorial into 3 factorial. So 4 factorial can be written as 4 factorial into 3 factorial into 4 factorial can be written as 4 into 3 into 2 into 1. So 4 into 3 factorial, which is same as this. We have written only up to 3 factorial because in the denominator we have already 3 factorial which can be cancelled. So therefore there is no need to write the full expansion of 4 factorial. Therefore 4 into 3 factorial divided by 4 minus 3 is 1 factorial and 3 factorial. So this 3 factorial and this 3 factorial will get cancelled and 1 factorial is 1. Therefore the numerator is 4. So let us solve the denominator. So 9 factorial can be written as 9 into 8 into 7 into 6 factorial. So 9 minus 3 is again 6 factorial and 3 factorial is 3 into 2 into 1. So the 6 factorial and 6 factorial gets cancelled. So 3 ones are, 3 threes are and 2 ones are, 2 fours are. Therefore 3 into 4 into 7, which is 84. 12 into 7 is 84. Therefore probability of getting all drawn balls as cricket balls is 0.0476. So the next sub question is, we have to find out the probability of getting at least one cricket ball. So whenever they have asked at least one event, then we can take the complement. So for this the complement would be 1 minus probability of none is cricket ball. So none is cricket ball means all the balls are of tennis balls. So we have to find out the probability of all balls are tennis balls. So 1 minus 5C3 divided by 9C3. Because there are 5 tennis balls, among this we are choosing 3 balls. So 5C3 divided by total number of balls, which is 9, and among them we are choosing 3 balls, therefore 9C3. So solve for 5C3 divided by 9C3, we will get it as 0.0595. Therefore probability of getting at least one cricket ball is 0.9405. So the 21st problem is, if probability A is 1 by 3, then find probability of A complement. So we know we can find out probability of A complement as 1 minus probability of A. Therefore 1 minus 1 by 3, which is 2 by 3. Therefore probability of A complement is 2 by 3. If probability of A is 1 by 2 and probability of A intersection B is 1 by 4, then find probability of B given A. So substitute it in the formula of conditional probability, that is probability of B given A is probability of A intersection B divided by probability of A, which is 1 by 4 divided by 1 by 2, which is 1 by 2. So these can be asked in 2 marks questions. So the 23rd problem is, if probability A is 1 by 8, probability B is 1 by 6 and probability of A union B is 1 by 4, then we have to find probability of A intersection B. So this can be done using the addition theorem. So just substitute all the values in the addition theorem and find out the value of A intersection B, which is 1 by 24. So the 24th problem is, if probability of A is 0.8, probability of B is 0.5 and probability of A union B is 0.9, find probability of A given B and are A and B independent events. So to find out probability of A given B, we have to know the probability of A intersection B. So calculate A intersection B using the addition theorem. So we have got it as 0.4 and now substitute it in the formula of the conditional probability. So probability of A given B is probability of A intersection B divided by probability of B, which is 0.4 by 0.5, which is 0.8. Here we can see probability of A given B is equal to probability of A. So we have probability A as 0.8. So in the definition of conditional probability, we had seen if probability of A given B is equal to probability of A, then we can say event A and B are independent. Also you can see this is probability of event A and in the denominator we have probability of B. So this is probability of event A. So when you cross multiply, we got probability of A into probability of B, which is probability of A intersection B. So we can say event A and B are independent. The 25th problem is, a fair coin is tossed 5 times. Find the probability of obtaining head in all the tosses and head in at least one of the tosses. So here we can't literally write the sample space when we are tossing a coin 5 times. It would be a tedious method. Therefore we can calculate small n with the formula 2 raised to 5. So when you toss a coin, the outcomes would be either head or tail, so which is 2 outcomes. So you're tossing it for 5 times, therefore 2 raised to 5, which is 32. Therefore there are 2 raised to 5, which is 32 equally likely outcomes. Out of them, one outcome is H, 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 H and H, that is all the tosses result in the outcome head. So when you toss a coin for the first time, you will get it as head. Similarly, when you toss for the second time, you get it as head, and similarly when you toss for the 5th time, you will get head. And similarly, there is an outcome where all the toss result in tail. So therefore we can find out the probability of head in all the tosses is 1 by 32, because there is only one outcome which is favorable. And the second sub question is probability at least one head. So there are so many outcomes which are favorable to the event, that is at least one head occurs. Instead of that, we can take complement, which is 1 minus probability of tail in all tosses. So at least one head means there can be one head or two head or three head or 4 or 5. So the complement of at least one head would be tail in all tosses. Therefore 1 minus tail in on one tosses, the favorable outcome is just 1. Therefore 1 minus 1 by 32, which is 31 by 32. Therefore the probability of getting at least one head is 31 by 32. So whenever the probability of event at least one has to be found, it is easier to find it by using the probability of the complementary event as follows, which is probability of at least one is equal to 1 minus probability of none. So you can use this note whenever they have asked at least to find out the probability of at least one, we can take the complementary event, which is 1 minus probability none. So the 26th problem is there are 20 persons, 5 of them are graduates, 3 persons are randomly selected from these 20 persons. Find the probability that at least one of the selected person is a graduate. So they have given there are 20 persons. So among these 20 persons, we are selecting 3 persons randomly. So this can be done in 20C3 ways. So since there are 5 graduates, it means the remaining 15 are non-graduates. Therefore, the probability of at least one graduate is 1 minus probability of none is graduate. That is by using, we are solving it by using the previous note. So at least one is asked, we are taking the complementary event, which is 1 minus probability of none is graduate. So 1 minus probability of none is graduate is, we can choose it by 15C3. So there are 15 non-graduates. So among them we are choosing 3 persons. Therefore 15C3 divided by 20C3. So simplify, we will get 1 minus 91 divided by 228, which is 137.228, which is 0.6. Therefore at least one graduate, the probability is 0.6. The 27th problem is, in a college there are 5 lecturers, among them 3 are doctorates. If a committee consisting 3 lecturers is formed, what is the probability that at least 2 of them are doctorates? So we can solve it in a similar way. So there are 5 lecturers, so among them we are choosing 3 lecturers at random. Therefore we can do it in 5C3 ways. So thus there are 5C3 equally likely outcomes. So let event A be 2 of the selected lecturers are doctorates, and event B be all the 3 lecturers are doctorates. So they have asked at least 2, which means 2 or greater than 2. So we are choosing 3 lecturers at random. Then event A has 3C2 into 2C1 favorable outcomes. That is 2 of the selected lecturers are doctorate. So there are 3 doctorates. So among them we are choosing 2. So therefore 3C2 and 2C1, which represents there are 5 lecturers, among them 3 are doctorates. So the remaining 2 will be lecturer who does not have a doctorate. Therefore among these 2 we are choosing 1, because among 3 we have already chosen 2 who are doctorates. So we are left with 1. Therefore among 2 lecturers who are non-doctorates, we are choosing 1 doctorate. So we can choose it in 2C1 ways. Therefore event A has 3C2 into 2C1 favorable outcomes, and event B has 3C3 favorable outcomes. That is, all the 3 selected lecturers are doctorates. So there are 3 doctorates and we are selecting 3 lecturers who are doctorates, which can be done in 3C3 favorable outcomes. So here event A and B are mutually exclusive. Therefore probability of getting at least 2 doctorates is probability of 2 or 3 doctorates, which is probability of A union B. So these are mutually exclusive. Therefore intersection term is 0. Probability of A union B would be probability of A plus probability of B. We had seen it in the definition of addition theorem for mutually exclusive. So probability of A union B is equal to probability of A plus probability of B. So we know probability of event A as M is 3C2 into 2C1 divided by N, which is 5C3, plus probability of B, which is 3C3 divided by 5C3. So simplify, we will get probability of getting at least 2 rates is 0.7. So the 28th problem is the probabilities of two students A and B solving problem are 1 by 2 and 3 by 4 respectively. If both of them independently try, what is the probability that the problem is solved? So let A be student A solves the problem and B be student B solves the problem. Then they have given probability of A as 1 by 2 and probability B as 3 by 4. So the complement would be student A does not solve the problem. So probability of A complement is 1 minus probability of A, which is 1 minus 1 by 2, which is 1 by 2. So similarly, taking the complement of event B, which is probability of B complement, which is 1 minus probability of B, which is 1 minus 3 by 4, which is 1 by 4. So the problem is solved when at least one of them solves it. So they have asked us to find out the probability that the problem is solved. So either student A can solve it or student B can solve it. Therefore, we can take the union. Therefore, probability that problem is solved is probability of A union B, which is probability of A plus probability of B minus probability of A intersection B, which is equal to probability of A plus probability of B minus probability of A into probability of B, because A and B are independent. So substitute the values of probability A and probability B. We will get probability that the problem is solved as 0.875. So we can solve this in another method, that is probability that the problem is solved is 1 minus probability that the problem is not solved. That is, we are taking the complementary event. So 1 minus probability of A does not solve and B does not solve. So the problem will remain unsolved when both A and B cannot solve it. So therefore we are taking the intersection. So A does not solve, we know it is as A complement. Therefore 1 minus probability of A complement intersection B complement. Here A complement is student A does not solve the problem and B complement is student B does not solve the problem. Therefore, since they are independent, we can take it as 1 minus probability of A complement into 1 minus probability of B complement. So we have got the values of probability of A complement and B complement substituted. So 1 minus 1 by 2 into 1 by 4, which is 7 by 8, which is 0.75. So in both the cases we got the same answer. So the 29th problem is the probability that a firer A hits a target is 1 by 3. The probability that firer B hits is 1 by 4. If each of them shoot at the target, what is the probability that the target is hit by them? So let us take event A as firer A hits the target and event B as firer B hits the target. Then probability of A is 1 by 3, which is given, and probability of B is 1 by 4. Let us take the complements, that is probability of A complement is firer A does not hit the target, which is 1 minus probability of A, which is 2 by 3. Similarly, probability of B complement is 3 by 4. So the target is hit when at least one of them hits it. So therefore probability of target is hit is 1 minus probability of target is not hit, which is 1 minus probability of A intersection A complement intersection B complement. So since they are independent event, we can write 1 minus 2 by 3 into 3 by 4, which is 1 by 2, which is 0.5. Therefore the probability that target is hit is 0.5. So the 30th problem is write down the sample space for each of the following random experiments. So a coin is tossed 3 times and the result of each toss is noted. So here the coin is tossed 3 times, which means 2 raised to 3, which is 8. There has to be 8 sample points. So 1, 2, 3, 4, 5, 6, 7, 8. So what are the sample points? Let us see. When you toss the first coin, you may get it as head, and the second time you toss, again you can get it as head, and the third time you toss, again we can get it as head. So the first sample point can be head, 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 and similarly the next possibility would be head, head, tail, head, tail, head, tail, head, head. Similarly, we can get all these sample points. So the second sub question is, a coin is tossed 3 times and the number of heads obtained is noted. So again you can, here they have chosen only the outcomes wherein heads are obtained. So there can be no heads, which is represented as 0. There can be only 1 head, or there can be 2 head, or there can be 3 head. So the third sub question is, a couple goes on producing children until a male child is born. The number of female children born is noted. So the sample space can be 0, 1, 2, 3 and so on. So in case 3 above, instead of noting the number of female children, the number of children born is noted. So here they have asked us to find the number of children born. So the sample space excludes 0 because here they are considering only the number of female children born. So there can be a possibility that a female child is not born. So in the third case, they have given the number of children born. So obviously there is either a birth of male or female. Therefore the sample space starts from 1, 2, 3, 1. So similarly try to find out for the remaining 3 sub questions. So that's it for today's class. In next video we will see about the random experiment. Thank you.